All right, today is going to be a brief summary and implementation of the ADAPT-QAOA algorithm, which is extremely similar to the ADAPT-VQE algorithm. It's not much like the ADAPT implementation. I did not have a huge degree of success with this. So yeah, we'll just get into it, I guess. ADAPT-QAOA has the same sort of idea, except you just basically you're optimizing the mixer. So at every step you um, prepare the complete superposition, apply the cost, and then apply one of the mixing pools or all of the mixing pool operators, and then select the one with the largest gradient, and then continue onward and repeat that process until that gradient is below a certain threshold. So yeah, basically, the default QAOA mixer is just the sort of x's, right? And so this is obviously, remember in QAOA, this is an exponent. This is an e to this power, so which is equal to rx. But that's not super important. Just looking at this, so then they propose two additional pools of mixers. One of them is sort of for single qubit operation, it adds y's, and single qubit, or just not the sum, but just individuals. And then there's also the multi-qubit operations, which add xx, yy, and zz operations on every set of qubits, every pair of qubits. And so you can see like the normal mixer of QAOA is a subset of the mixer of the single qubits, is a subset of the mixer of the multi-qubits. So that's the sort of the brief overview of it. It's pretty straightforward, right? You just say, you try all the different mixers in the pool and pick the one that has the biggest gradient and continue onward. Basically the same as ADAPT-VQE. However, I did not get great results with it before. But basically looking to recreate figure 1 in the paper, which of course will be linked below. And the reason, I'm not entirely sure. I think the reason, I don't know. I don't entirely know the reason, but I'm also skeptical of some of the, some of this information. I don't mean to like, I'm not skeptical. I'm confused. I don't want to sound accusatory here. But they have a loss function basically that goes 10 to the negative 10th is the energy difference between the target, like the real energy, and the QAOA predicted energy, which doesn't really, if you're optimizing it down that much, it doesn't seem to make a lot of sense to me, because for floating points, like float 32s are only precise up to like 10 to the negative 6 or something like that. So I don't know, just maybe they're doing larger floating point representations or something, but just a little confused by that. But anyway, getting into the code, this is sort of blitz overview we're doing right here. So we have our usual imports. We have TensorFlow, TFQ, circ, all that good stuff. We have a helper function to convert these list of binaries to integers, and then we create our graphs. So in the paper they present two 6-node graphs. One of them is a complete graph, the other is a cycle graph with additional edges, and so we just create them using network X. And then we have our standard mixer and cost Hamiltonians. For the max cut problem, we have the Rx here, and then the C0 RZ C0 right here. We create our cost function for this weighted version, which is the 1/2 ZZ operation. And then we also have our this weight, right? Because we can have weighted edges. And then I'm just checking something real quick. Yeah, okay. And then we have our circuit that we're creating for normal QAOA, where we initialize this complete superposition. This is all just copied from the QAOA v2 video, so check that out if you want more on QAOA. Oh, interesting. And then you create the cost and mixer Hamiltonians for the depth and return it. And then we create the model. So we have our input of data type string, our circuit, our cost function, and then we have just defined as a model. We train it by just directly minimizing the output. Oh, I should do that actually. And then we have this ADAPT-QAOA. And so this is the big difference here. Okay, so in this one, we first create our expectation layer, defaults to adjoint differentiation. Note that this is a difference from the paper. I think they use Nelder Mead, but yeah, that's neither here nor there. And then we have the iterations and tolerance that we're optimizing for. We create our initial circuit with the equal superposition, initialize our optimizer, and create our cost function. And then we first create our first cost layer as our base circuit, and then we iterate through this however many times until the gradient is small enough, right? We have our, until this gradient is too small, there's no gradients large enough, we iterate through here. We append parameters and symbols to create this. We generate our circuits based on the operator pool. So we take the exponential of this operator pool and then just add them for each circuit. We get the gradient, so we just take the expectation of this operator for the given circuit, take the gradient, get the average of these gradients for the last however many we've implemented. I realize now that that is probably a mistake. Yeah. I think what we want is inner counter 0. Inner counter plus equals 1. And then we want inner counter here. And then I will, 1 second. All right, I fixed that. That's that was just a minor typo in the counter. So basically we look at the last gradients for this specific layer, right? Because we're going layer by layer, cost function wise, and we're creating the mixer at each of these layers. And then we optimize this circuit in between every time we add a gate or a operation. So we repeat this process until the options to add choices or the options to add operators from our operator pool are not impactful enough. And then we break, and then we move on to another depth for however many depths we have. And then we, this just generates the real cost of, so we can calculate the error. So it just generates every possible cut and then finds the optimal one and then calculates that cost. We define our single qubit operator pool here, which is the sum of all x's, the sum of all y's, in addition to the single qubit x and y operators. And then we have our multi-qubit pool, which is the S pool, single qubit pool, in addition to the XX, YY, and ZZ operations on every possible pair of qubits. And then we create our random graph, get the results for each of these, the errors here, minus the solution, and then plot them. And what we see in this plot is a log plot here that is not as compelling or as the original paper, which is interesting. It's not interesting that my implementation of their results doesn't do that well. I'm sure there's things that could be optimized, but it's interesting because my QAOA significantly outperforms theirs, getting error rates of orders of magnitude less with many less layers. So it's just interesting to note. I don't think this implementation is entirely reliable to the original paper, but I think it is pretty much correct from a big picture standpoint, so you can sort of manipulate, do what you want with it. There's some open problems in the future work section of that paper, This has been basically a blitz. I think this is my fastest paper review yet. I don't have a lot to say about this because I don't have great results. So I'm just I wrote this code. I want to get it out there. Maybe it'll help someone. So yeah, that's all we're going through today. As always, check out the code and the paper in the description.